Yeah, okay. Glad to see you all back. We are now heading for an ambitious thing because we're now going to work until 6:45. Six presentations, quarter of an hour each. And it will be two topics that are really very much important to CCUS. It's the monitoring and it's the cement. And we are kicking it off with the monitoring, and we have the Ensure project here with Bettina Gertz-Allmann. And she is explaining us all about this Act 3 project that's just started last autumn. Bettina, the floor is yours, and please try to be within 13 minutes.
Yes, welcome, thanks, and I will try my best. I understand it will be hard to follow at this time of the day, but no, this is not my project, but I would not do a very good job here, so. Yes, that looks better. Thank you. My name is Bettina Gertz-Allmann. I'm a senior researcher at NORSAR. We're a research institute located just outside of NORSAR, outside of Oslo. And I'm happy to present the Ensure project on behalf of all our partners here. Ensure stands for Effective Monitoring of Long-Term Site Stability for Transparent Carbon Capture and Storage Hazard Assessment. It's a very focused project all about microseismic monitoring and also communication strategies. Let me start just with a general statement on microseismic monitoring of CO2 storages. Microseismic monitoring has a long-established method for the surveillance of subsurface activity, and it's known that the seismicity shows where the fluid pathways and stress transfers are generated by the injection. There are still several challenges. Microseismic for CCS monitoring has still a mixed acceptance level, and often due to insufficient aperture or sensitivity. So the estimation of more advanced parameters is therefore often limited by the data. And it's also challenging to compare the effectiveness of microseismic monitoring for CL verification between sites. There's lots of development and large success stories in terms of microseismic monitoring, for example, at the Decatur site in Illinois or at Quest in Alberta. And also distributed acoustic sensing is now a very promising tool for microseismic monitoring, but it's still in an early stage and more needs to be done here. The overall project aim is progression of microseismic monitoring technologies to become a robust, cost-effective, and publicly accepted tool for seal integrity verification. Our main objectives are recommendations for design of fit-for-purpose and cost-effective networks, improved understanding of the seismodynamic behavior, and identification of most relevant seismological parameters, and finally recommendations on how to share this rather complex information with the public or stakeholders, and how to educate on real versus perceived risks of induced seismicity. So to maybe come back to Ranghild's why and how The Mission Innovation Report clearly states that unmitigated induced seismicity is still a critical knowledge gap, and we believe our project can help to close this gap. And it was also mentioned several times yesterday that how important trust is in the end, and of course monitoring will help to gain trust, effective monitoring, and also the right way of communicating it. Some words on more innovation potential of the ENSURE project. ENSURE is one of its first data-driven studies, so really data-driven. We work with lots of data, and to study quantitatively and assess and optimize microseismic monitoring for integrity verification. We will have access, or we already have access, to a large set of monitoring data, including surface downhole geophones, in-well and surface dust cables. We can then compare data not only within sites, but also across sites in different places. And we certainly aim to gain new insights into detectability of microseismic events with fiber optic data, and will investigate how to optimize the array configurations. Innovative methods will be used to analyze the acquisition footprint on seismological parameters, and also international comparison on conditions and strategies for enhancing public acceptance will be investigated with sociological surveys. This will be done in various countries. 9 partners form the ENSURE consortium from 7 different countries. You see here partners from Europe, as well as the US and Canada are involved. 3 partners are funded via ACT. This shows an overview of the case study sites that are included in the ENSURE. Quest, Alberta, with lots of valuable data, as well as the Decatur site in Illinois. We have access to data from the Dover 33 in Michigan, data from southern France, as well as southern North Sea and Norway. It was already said, this is an Act 3 project, so it's still rather early on in time. We are in Q3 of the first year. Not too many results yet. The web page that's listed here is also rather preliminary, and we are working still on a separate project web page that should be coming out soon. Here you see the structure of our project with only 3 work packages. So as I said, rather small and focused. Work package 1, it's about field scale testing and also new data acquisition. Here we acquire data, for example, at the Quest site with a downhole fiber. And we will develop novel analysis tools, including noise assessment between all the different sites and sensors, and then compare the sensor technologies and their network setup. Within work package 2, it's more about interpretation. The main questions to answer here are what seismological parameters should be communicated and which analysis should be performed. This is also done by analyzing the influence of network properties on these parameters. And then in work package 3, it's how do we communicate? So this is led by social scientists of the University of Alberta, and as I said, we will develop some communication strategies to communicate about induced seismicity to the public, but also stakeholders. since I can't really show a lot of results yet, I will go about 2 case study sites, a bit more detail background, and show a data example. Quest, you're probably all familiar with the site. Here in Alberta, 1 million ton of CO2 is injected every year in 3 wells. The injection wells are shown here in the lower right. And this site is operated by Shell Canada. They started injecting in August 2015 and are injecting since. It took about 9 months before the first microseismic event was detected. But since there are about 100 events every year, and you see a set of seismicity here on the lower right, the colored dots. About the monitoring, we have, as I said, quite lots of monitoring available here. There is a downhole geophone close to the middle injector, and there's also a fiber cable in the injector reaching down to 2 kilometers. And in addition, there is now, read recently, surface nodes installed, about 150 nodes distributed here at these triangles in different patches. So the events that you see here, they are all located within the Precambrian basement, so not in the reservoir. But there are still uncertainties about locations, and we still need to further address also the question of location uncertainty. I just want to show one example of data here. This is the fiber recordings from a magnitude 0.8 earthquake. We had some issues with laser noise in the beginning, so in the raw data, it's rather difficult to see anything. This shows distance along the fiber on the horizontal versus time on the vertical axis. And if you apply some filtering, just a simple bandpass filter, it's still noisy, but you start to see some event. And if you apply more advanced filtering, like singular value decomposition, you start to see like the P wave and S wave arrivals, including reflections, and we also start to see converted phases. So we will be able to really use this data for further interpretations. The other site with lots of data is southern France, here located at the Disco site, the former LAC production site. Here, all different kinds of sensors are placed at different locations here at these different sites. There's also a fiber cable in the pond with different types of cables installed. And this is really ideal for what we plan in terms of comparing technologies. This is my final data example. The data of the DAS, shown here on the left, of a magnitude 2.5 earthquake, so not that small anymore. Quite noisy, but in some parts you see the P wave arrival here, and then S wave arrival, and also in comparison the geophone data on the right. So outlook, we are now really working on finalizing the survey questionnaire for work package 3, working hard together, involving also all partners and other stakeholders. And we continue the data integration, and still acquisition is ongoing as part of work package 1. And we start up work package 2 now with initial modeling to analyze the network footprint. And with this, I just also want to thank ACT and the individual funding agencies and all partners involved in this project, and very excited about results coming out of it.
Thank you very much, Bettina. I think there's time for a quick question if somebody has one. Yeah, Philip.
Thanks. Thank you for your presentation. So my name is Philip Nelen from TNO. actually have two questions. I'll start with the first and see if there's time. In your presentation, you talked about communicating your results. And then you started talking about social scientists. So I thought, okay, that's probably communication to the public. And then, so my question is about communicating results of monitoring CO2 storage projects to the relevant authorities. Is that something you consider in your project? Are local relevant authorities included in your project? Do they look at the project to understand what's happening?
Yes, this is the goal. So it will involve also reaching out to local authorities and public as well. Yeah. So, but with really a focus on the induced seismicity monitoring aspect.
Can I have time for a second question?
Yes, go ahead.
Thanks. Personally, I'm very interested in uncertainties in all of this, monitoring, comparing monitoring data with expected outcomes. You said a few words about working on the localization of events in subsurface. To what extent are you going to work on that? Will you include all of the geological uncertainty in that?
We certainly will address the point of uncertainties quite a lot in terms of also the modeling aspect. And the plan is that all different types will flow into this. So yeah, since we know that the uncertainty is rather large, we also need to evaluate what can we expect or what can we accept on location uncertainty. If we would only have one sensor setup available, or is it required to expand on this, and how much will we gain from combining the different technologies, and where's a limitation? How far can we get with what we have, and what might be required in the future?
Okay, thank you very much, Bettina. And we're moving on in this session on monitoring, and the next speaker is Guttorm Alendal from Actom project, and he will tell us all about it. It's an Act 2 project, so he has results there.
Do I? Probably some. Let's see. I'm presenting this project that's maybe been the most fun project I've been involved in, because we are really cross-disciplinary. So if you see the group of people down there, they are coming from professors of law, geomechanics, and ocean chemistry. Me, myself, I'm an applied mathematician trying to look into this. So we call this ACT on offshore monitoring. So we use this ACT as a verb. I will come back to why I'm a bit disappointed that that's not happened yet. I move forward with this one. Yeah. So we are 8 partners in 4 countries. And I do this first, so I remember to do it. So we really thank the funding agencies for us to work on this project. It's been really fun. In addition to this very competent group inside the project, we also have a very competent advisory board that we will utilize more at the end of the project. I would like to just a little bit of motivation before I come to results. So this cheese hazard model is very disputed, but it's still a way of model or just demonstrate what risk is. So you put layers of layers. If something goes wrong in one layer, it's kept in the next one. So hopefully there will not be a hole all the way through so that you have losses or something that you don't want to happen. So here we have like an electrical system in your house. You have fuses that shut down everything if something's happening. You make sure that all your system is according to it's healthy and there's no fires coming from that. And you also have mitigations. So if there's something happening, you can pull out that fire. And then, of course, if worst thing happen, you have an insurance. And this is, I have to send this a bit earlier, so these are US insurance companies. I was planning to change them to European, but because I used this in New Orleans a couple of weeks back. But there's one thing missing, isn't it? What's missing in this slide? Monitoring, isn't it? So the insurance company is not going to allow you to only have those three in place. There's some sort of monitoring in the fuse, of course. Unless you have this in place, they will say, no go. So we need monitoring, okay? That's my main message. So what we want to do is to look into, we talked about uncertainties there. This is like, if something's going on, there's a fire in your house and you detect it, then you have true. That's good. It's not good because you have a fire, but your monitoring capture it. If the monitoring is quiet, but there is a fire, then you have this false negative. Okay? I'm not looking at, I'm not detecting it. It's like when Trump said, why don't we stop testing people? Because then the COVID will go away. So we need to look, and we need to avoid false negatives, because that's, if you talk to socials or talk to the community, if you're not looking at the right place and can document that, it could be a problem for you later on. If somebody else detect a fire and you haven't seen it. Then, of course, if everything is quiet and there's no fire, there's no leak, then we have the false. And, of course, we have the true positive. That is, I detect something, but there's nothing there. I remember living in a flat where this smoke alarm went off every time you tried to make some food. That was a false alarm. And we have examples, for instance, from Tomakomai, I never managed to say that, where you have false positive, somebody else detects some anomalies, and you have to go out and explain it afterwards. That's a false positive. We need to avoid that as well. So that's why we have this looking at the lamppost. We need to look at the right place for this, and we need to document that we are looking at the right place. So then I need to show this, because I use work like leakage and environmental impact and stuff like that. That doesn't mean that you think this will happen. This is to make sure that we are prepared, that questions might rise that we need to answer. So let me make this clear. I'm not saying that there will be a leak, okay? Okay, Actom project. We have been running for, it feels like a lot of years and a lot of Zoom meetings. We have, until next February, we have an extension. So work package 1, we put together a professor in law with an chemical oceanographer, and a technical sort of instrumentationalist, and they work together. The purpose there was to look at what can we measure and what do they want us to measure from regulations and legal aspects. Then we have work package 3, using the responsible research and innovation thoughts into CCS. And there we have Dorothy Dunkel, that's working from bio, and marine environment, working together with a lawyer again. Today I will mostly talk about work package 2 and work package 4. Work package 5 is why I'm here. That's just the integration part. So the main purpose, this is working, isn't it? We had over many years in many EU projects worked on different tools of how to simulate if the CO2 reached the marine environment. We figure out we should pull all of these together and make a toolbox out of it. Then we added the legal part and the social part on top of that, so that this toolbox answers the right questions. So this was the toolbox when we did the application. Today, it looks like this. So now I have, how much more? 7 more minutes, and I will go through one. No, I won't. What this is, what you see up here, there are 3 sort of main input that we need to this toolbox. I will explain shortly about them. Then we put them through different sort of number crunching. That's where I'm living. And then we come out, we want to have a report helping the government or the operators to look at a specific site. So this is very site-specific. I'm going to look at and demonstrate this now on the Gulf of Mexico, where we have been working mostly, and that was because I went to the US a couple of weeks back. So there it is. Luckily, we found a place here where we could find all of these 3 kind of data. So this is a site we choose. This is not the site where they plan to do anything. It's close to a site where they sort of think of doing stuff in Gulf of Mexico. But we are demonstrating this in this site of Houston. So what we have here, we have, we can do the geophysical characterization. There was a P-cable test out there. We know what's underground. We found this local coastal model that could give us the velocity files. And there was also these geochemical measurements out there. So we found them all in one place. That's why we picked this place. So this is not to do anything on a storage site. It's for demonstration. So what we need, based on the characteristics of the underburden, we need to say, if it's coming up, where is it most likely coming? That is where we should put the lamppost. In addition, so here we have characteristics done by TNO. We have shallow gas pockets. We have fractures and all of that's things that geological people talk about. We are mostly interested in what's happened at the surface, the seafloor. Here we have a map of all the maps, wells in the area. Those are most risky areas. And then, of course, we have, I'm trying to follow the time. Oh, you. So each of these will be a risk point. And then we can use this in the next, push this button. It has reached the seafloor. It's been transported by the velocity and also a lot of other events in the ocean. What we have here now is, those of you that's into math, this is a linear equation. That means I can take each source individually and I can simulate that one. I can scale it, I can multiply it with 10, divide by 10. It's still the same result. And I can take the next source and add on top of it. So what we're doing, we're running each of these risk points separately. Then we can add and use ensembles on top of that. So based on those results, we can build time series like this, where we have influence from each of these points at the specific point. So if I'm there measuring, I can use these time series to see what the time series will look like in that point. Okay, sounds good, doesn't it? The problem is CO2 is naturally out there and it's not constant, it's varying. So when I show that video, it's going to be blurred. And that's something I didn't manage to do because you wanted the slides really early. What we have is we need to see what's the variability of that. And here we have 2 methods. So we have CSEEP looking at a stoichiometric method, looking at the other processes there, and what's not explained by that will be an indication of a leak. And we have a rate of change. And this is one of the problems we have. This one reads high frequency measurements, and those are really rare for seafloor. That's something we need. I need to move on. Yeah, so then we need to add that on top. So we have 2 probability distributions. We need to sum them together, and then we can, based on that, suggest where you want to measure. So then we can do this. So these are, here we have, this, as I said, this will be blurred. It will be hidden between a lot of noise because there's a natural variability out there. Based on that, we can see where we want to place measurements. And the numbers inside of this is how many wells they will monitor. So that's something we can do. We can also see how big area will be influenced by a certain pH reduction. And as you see behind there, it says demonstration. So this is demonstration. This is not something, these numbers is not something you're going to cite me on, okay? They're in there for demonstration purpose. That's probably end up with a report. Probably it will. I'm thinking probabilistic. Okay, let's, where we are, the site studies. As I said, Gulf of Mexico, we are more or less, we need to talk to how to design these studies. What we really need is high frequency biogeochemical baseline. That's missing for the seafloor. The Norwegian side, there's a very good map at the Petroleum Directorate. We can get all the locations we want. There's an operational coastal current from the meteorological office. We're still missing the baseline for the chemistry. P18, we have the geological map in place. We will find the velocities. We still need this one. We haven't started on the UK side yet. And we are working on GT 16, so we have a couple of months more to work. So what we want to do is to use this for communication purpose. And now let me just, what we really want to make sure is that we can communicate that this is the way we're thinking. We need to put out this. And if I can make a personal comment, I'm a bit disappointed with the Northern Light project, where it's an industry project, I understand that. And there's not going to be anything happening because they found the safest place to store it. Still, we are missing what we need. It should be so cheap if you're out there with a boat to put down a lander and get that time series for us. But it's very hard to get it done. So that's an invitation to anybody that has something in the North Sea. Please give us this time series. And another thing is, we are in the ocean decade. There are so many people out there doing measurements, and they can see something that you don't want them to see. So you should be there first. I'm stopping there. That was the last one, wasn't it? Yeah.
Thank you very much for your clear presentation, and also the promise to tell us more about the results at GHGT in Lyon this autumn. Looking forward to it, and looking forward also, give him a hand, and we'll go on with the next speaker. It's Arvid from DigiMon project. Arvid, the floor is yours.
Well, thank you. I will take this opportunity to share with you what we have been doing in the DigiMon project for the past 2.5 years, 6 months to go. These are the project partners, a number of brilliant institutions, and particularly being here in Rotterdam, I'm very proud that also TNO is part of this team. So I think they are really contributing very strongly to this project. So let me look at this one. Okay, good. This is the initial cartoon that we used for the proposal. And it's simple, but it is really as valid as it was 3 years ago today.
I must ask you to...
Oh, sorry. I have to stand before the microphone. I know. I should have known. Wonderful. So this cartoon now was the cartoon we used for the original proposal, and I thought I would start with that today for several reasons. One is to state what the actual objective of the DigiMon is. This cartoon is showing a very simple sketch of, imagine this is the sea floor, you have the sea surface here, and this is the subsurface. So basically what this project wants to do is to look at ways to monitor what is happening with the CO2 plume in the reservoir, and also to monitor what's happening in the overburden. So developing techniques to prevent CO2 from escaping the reservoir. So bluntly speaking, our ambition is to put Guttorm out of business. Because if nothing comes to the surface, then we don't have to worry. So sorry, Guttorm, that was maybe a bad joke. Anyway, I think monitoring the subsurface today, we do that in the oil and gas business, and there are numerous systems to do that. But if you are going to do this the same way as we do for the oil and gas business by, for instance, putting out permanent reservoir monitoring systems at the seafloor, it becomes very, very costly. And it's not something you would like to do or that maybe you can afford if you have a reservoir that is very extensive and the migration of the CO2 is very extensive because it becomes very costly. So the idea of this project is to combine low-cost, multiple measurement techniques into one system to try to get the same answer as you could with a potential more expensive system. Yeah, I think I'll just move ahead. And why then is this important? Well, in order to have a license to operate a CO2 storage site, you need to convince the regulator that you have a good system for monitoring the reservoir in place. So that's a very sort of firm requirement, and that's something that nobody can escape. So what have we done now in this project? Well, we have kind of assessed a monitoring system composed of multiple monitoring techniques, measurement sources, data types. And we have organized this in the way that our first work package has been looking at the very basic measurement technologies. And one key technology is using fiber optics for both acoustic sensing as well as for chemical sensing. This slide here is about the field experiments that we've carried out in the DigiMon project. Luckily, as the pandemic hit us, we got access to early data from Antarctica that the University of Bristol with Mike Kendall brought into the project. Because if we hadn't, we would have been in trouble because our field campaigns was deferred by 1.5 years relative to our original plan. So that made us, then we had some data to work with. And the Antarctic data was very good in doing the initial work in the project. But now we have also been able to complete the 2 original field campaigns that were outlined in the project. One in Canada in the Field Research Station in Calgary, and the second one in Svelvik in Norway. And the key output in this first work package is processing algorithms for the distributed acoustic sensing, and also algorithms to acquire and process gravity and deformation data. As well as we have also performed feasibility studies of how to use and using distributed chemical sensing for CO2 leakage monitoring. So that's the kind of the hardcore work, basically, of work package 1. Then work package 2 has been a combination of assessing the technology readiness level for a number of these techniques that are involved in the DigiMon project, as well as setting up both a forward modeling framework and also an inversion framework for a selected case at Smeaheia, whereby we try to invert on different data types to see how sensitive they are with respect to measuring. And this first case that we run, we look at the saturation. So we look at how sensitive different data types are when it comes to CO2 saturation in the reservoir at this particular case that we have developed. Here we are looking at both ordinary seismic data, distributed acoustic sensing data, gravity data, and seafloor deformation data. So we are trying to combine these in order to get an answer as accurate as possible of how the plume is behaving. So the illustration at the lower side of this graph, or the slide, is the framework that we use for inverting the data. The table on the right-hand side is a table showing the technology readiness assessment of the different components of the system. And the key output here, I already said, we have developed this forward modeling framework that we use in the project, and also, as well as an inversion framework, a methodology how to invert on multiple and different data types into a single system. And now we are conducting the final sort of deliverable in this project, which is to develop and optimize or a methodology for optimizing the monitoring solution that also includes, in addition to the geophysical information, also includes information about societal acceptance or embeddedness, as we call it, as well as economics, the cost of the different systems. So this is something we have been discussing now within the project, and also with our industry partners. So we're about to complete that over this summer. Then our third work package is something that we are very grateful to TNO for, simply because they brought into this project a new methodology on looking at the societal embeddedness of a technology. And this is different from social acceptance, which I don't like, really, to be honest, because it's just far too simple. The methodology here, developed here, which is called the societal embeddedness level methodology, is a very precise methodology that measures how embedded a technology are in society, parallel to how ready it is from a technology point of view. So basically what we've done is to develop a system on a scale of societal embeddedness or parallel to the technology readiness level. So by doing this, we have been able to actually develop this into a very quantitative way of looking at how are you actually anchoring and embedding a new technology in society. And we have received a lot of positive feedback for this methodology. Then why and how has DigiMon contributed to accelerating CCUS technologies? That was one of the questions we were supposed to answer during this workshop. So I think we've done that in several ways. Number one, I think this interdisciplinary socio-technical approach that we've taken has proven very successful. I think also the fact that we have attacked this from the very basic, point that we have matured core monitoring technologies like distributed acoustic sensing, distributed chemical sensing. We have developed a framework for integrating multiple monitoring technologies and data sets. And we have developed frameworks for forward modeling, inversion, and optimization, as well as we have developed methodology for embedding CCS and CO2 storage in society. The way we go about dissemination in this project, I haven't listed a number of publications, but I just wanted to show on the right-hand side what we have developed as our dissemination plan, which really specifies to partner and for what we want to do now in the final phase of the project. So here you can see a list of 15, 20 different dissemination activities, events that we want to carry out during this final year of operation. So I think that's my last slide. Thank you for your attention.
Yes, thank you very much. I have to adapt here a little bit. Well, I wouldn't deny the audience the possibility of a quick question. Yes, we have one here.
Thanks very much for the presentation. Sana Garcia, Hergot University. My question has to do with the ACL methodology. So two questions really. The first one is how do you quantify the engagement of society or the embedment of society? And the second question is what's the granularity of the platform? I guess my point there is to what extent you differentiate between technologies in order to communicate that to the general public. Is that something that we need to do, or shall we stay more at high level in order to get the message across? Thank you.
Well, just to answer your first question, maybe I can just go back. No, I can't because it's off. But in one of the figures I showed, there was a list of different cell levels. And the cell methodology is something that is quantified just by the way it's structured, because it points to different parameters that you include in this societal embeddedness concept. And it says something about, on a scale, how mature is this from immature to mature to kind of societally accepted. So in a way, it has an inherent structure that makes it sort of quantitative, not by a mathematical number, but at least in sort of process context, if you like. And then your question was about the cell methodology as a framework, and how do we use that? Well, in DigiMon, we would very much like to use that to help us create the narrative and the final narrative for the project. Because I think DigiMon experienced what all projects experience, that we set out with a course to do a number of things, and we have managed to do a lot of them, but also we see that we have adjusted our course as we move along. And I think also we see that there's a very clear need to develop a narrative on the project. And we think the cell methodology is a very good tool to help us develop that narrative. And third, the cell methodology has been excellent from an internal project point of view, because it has enabled sort of technical scientists and social scientists to sit down around the same table, talk to each other, and actually ask one another, what are the critical points, when it comes to developing a system like this? And what are the critical points for communicating what we are doing out to the bigger audience? So I think it has been beneficial in a number of ways.
Thank you very much.
That's a long answer.
Yes, I was also going to refer you to further talks during the drinks. We thank you very much, Arvid. We're now going into cement industry. It's an important industry for CO2 management to think about cement, and we have here Colin Snape from ABSALT project. It's an Act 3 project, and Colin, please let us hear all about it.
Thank you very much for the introduction. If this talk looks rather hurried, there's a very good reason for that. I'm supposed to be on an aeroplane at 9 o'clock. And I think I first of all need to thank Ragnhild, and I don't know who you are, but representatives from ANICA and Create. Thank you very much for letting me jump the queue, because I'm certainly not going to be allowed to do that at Schiphol Airport. So I think the other slide put down, even though this is in the cement section, what I'm going to be talking about, essentially solid adsorbents, are completely applicable across a wide range of applications, and probably in the short term, direct air capture is probably going to represent the biggest market. So in terms of partners, each of I look down rather than look up. 3 from the UK, University of Nottingham, PQ Corporation. PQ Silicas are a multinational company, one of the largest manufacturers of silica in the world. BASF from Germany are singly the largest manufacturer of polyethylene imine, which is what we're majoring on in this project. The cement link comes from Cemex, and clearly we're going to look at integrating this technology with cement plants. University of Ulster, and just to say I'm not alone here, even though I need to rush off at 5:20. Let me introduce Yi Huang from University of Ulster, who will answer any questions you might have later. So Yi is really covering techno-economics, life cycle analysis, and risk assessment. So really, let me cut to the chase. What is our ambition here? And it's really to push forward the development of silica polyethylene imine. This is a bit of a mouthful. Solids adsorption looping technology. Basically, we are confident we can drive down costs, optimize the composition through everything we're doing on the project. What's of relevance is this picture. Sorry. Pointers packed in. This one here is the biggest solid adsorption plant that's operated in the world. This is in Korea, and we do have a very strong link with Korea Institute of Energy Research, who've actually operated this particular plant. Other partners, last but not least, University of Bologna and Centre for Research and Technology, HELLAS, I think I got the pronunciation right, SURF in Greece. Right, some background, and really what I'm trying to convince you, we've been doing this a rather long time, and you might say, like, why do you think now we can make a big leap forward? And we've looked at this system previously. You can tell this is an old slide because it's on power plants, it's not on industrial processes, but as you do with any new, what you might call second or third generation, you really need to do some initial sums to see where you're likely to come out against aiming scrubbing. Should just say, all we're looking at here is the regeneration energy, and at the time, and we took a very conservative approach, because obviously in this sort of exercise you can end up with a large range of uncertainty, but literally we took the worst performance we would get from this system, and it came out looking fairly good. One area where you gain is sensible heat, because as you all know, water's got very high heat capacity. Solids don't really cause corrosion, so that means you can go with very high loadings of material. And yeah, the sums at the bottom give you the potential for advancing over what amine scrubbing can do. So, other part of the background is solid adsorbents. The literature is huge, thousands and thousands of publications, and as I often say, really to paraphrase Winston Churchill's expression, never has so many papers been published on so little material. And really, you've got a huge valley of depth between what you see in the literature and what has progressed through the valley of depth to a pilot scale. And yeah, I don't have time to run through all these materials, but on top of that, you've all heard of MOFs, but all everybody looks at to get publication in high-quality journal is what is the CO2 capacity, and that essentially is only the start of the story. So really, what you have to consider is everything on the right-hand side, particularly cost, engineering feasibility, stability. Moisture co-absorption is huge. Your material might be tolerant to moisture, but if it also absorbs moisture, your regeneration energy literally shoots through the ceiling. So stability, there's a whole range of factors, and on any of these, your material may fail. So essentially, that's our mission in ABSALT for Silica PI, and I've just given a very simple representation of a project in terms of who's doing what. So PQ Silicas are working on silica selection and properties. BASF are working on polyethylene imine. We are doing a whole bunch of screening tests, which will feed through to pilot scale activities. And also because we've heard from, sorry, I'm hopeless at acronyms, that's why I've got my crib sheet up here. But in launch, we heard about amine degradation. So clearly, polyethylene imine can degrade. And work package 5 is looking at worst case scenario. If adsorbent does degrade, what can we do to regenerate it? And then we move on to what Yi is doing in terms of techno-economics, high-level demonstration plant design, and environmental life cycle analysis. So essentially in this project, we're working at a scale of tens of kilograms, and really, we really want to de-risk the next stage. Can we scale up to literally scale of tens and tens of tons, which is essentially what you need to be operating at roughly 1 to 10 megawatts in terms of equivalent electrical generation. So there's extensive links between the work packages. Sorry, for one thing I haven't got is a team photo because we've only been able to meet virtually. So next meeting I should be able to show you a picture with all our partners. Sorry, but I don't know. Oh, it's fair, yeah. So all I'm saying about the time scale, when we put this together, we talked to our government representatives. They said, yeah, they said, Colin, this is all about acceleration. And I said, yeah, if you can do a 2-year project, that will really show your ambition. I must admit I'm a rather cautious driver at my age, so I'm not used to hurtling down autobahns at 100 miles an hour, but it really feels a bit like this for this project, where we condensed it into a 2-year time frame. We actually got all the agreements signed in January, so we've only been going literally 4 months, and the end date, if everything goes to plan, will be February, March 2024. So let me just run through very quickly some of the things we've been doing on silicas. We're just trying to look at the trade-off between CO2 absorption capacity and attrition resistance. It turns out these materials are pretty good because polyethylene turns out to be a natural binder, but we are looking at the deal where essentially its mesopore volume represents the amount of PI we can get on the adsorbent. This slide is important. This graph on the left-hand side just shows, certainly at industrial process temperatures, 60, 70, 80 degrees, kinetics are super, super fast. And clearly what we're looking at is the trade-off between reduction in CO2 activity and strength. PI, the key thing we're doing is there's basically 3 types of nitrogen, NH2, NH, N, primary, secondary, tertiary. We're reacting the primary amines to improve stability. We're looking at a whole bunch of parameters, but if I can just show you the big breakthrough we've made so far. Yes, skip that slide. So basically what we've published a few years ago is the purple bars, and we've done pilot scale tests, and yeah, the material didn't last that long. It underwent thermo-oxidative degradation. We know the reasons why, but we've just actually improved simply how we mix things together, and just by coming up with better mixing, you can see we've stopped, virtually eliminated oxidation. And if we do a low degree of what we call alkoxylation, just a low conversion of primary amines, look at this. You know, we've actually stopped oxidation. This is under dry conditions. Under process conditions, you've got some moisture there, which acts as a protection. So we already know that this material will last and last and last for a period of years and years. And the bottom line is just driving down what is your replacement cost for adsorbent. Yeah, this is a pilot scale facility. This is at the University of Nottingham. Yeah, time's running out, but basically this is operating on 5 to 20 kilograms. It's quite funny, this rig was just built before the lockdown, so we're just in the process of commissioning it, and pilot scale tests will commence in the autumn. That takes me on to what will happen, which in this case it's not going to, if the polyethylene imine degrades. What we've done with Bologna and SURF already is demonstrate you can actually convert the degraded polyethylene imine into valuable products. You probably haven't heard of pyrazines before today, but they are a valuable class of flavouring compounds, and they do have high commercial value. And clearly, if you degrade pyrolyze the PI, you can actually regenerate the silica, which is obviously contributing to reducing your adsorption costs. Yeah, time is short, yeah. So just to say, techno-economic life cycle analysis underway. Ye has already done the baseline case for a cement plant. These are essentially performance indicators we're looking at, so I don't think there's anything unusual, out of the ordinary there. And final 2 slides, when we'll advance, is life cycle assessment, and that's come up in other projects. You know, we really need to know about all the associated CO2 emissions. And finally, and this is really what I picked up on yesterday, is both financial and technological risk are huge factors, and clearly recent events in Ukraine have amplified the need for this study. So, yeah, that's all, folks. I'm going to have to rush off now, but you will be around for tomorrow and answer any questions you might have. Thank you. Yeah, 15 minutes. Actually.
Yes. Thank you very much, Colin. Don't forget this. This is yours.
Oh, right, my crib sheet. Yeah, I can never remember acronyms.
That was really great, and it's good to know where we can address our questions. The next presentation is from the ANICA project. It's by Jochen Ströhle. He is the only one who is on stage 2 times today. Jochen, take it away.
Okay, thank you so much for the introduction. So I don't have to introduce myself again, I think. So this project is also coordinated by Technical University of Darmstadt, and we have 3 countries involved. That's Germany, the UK, and Greece. It's about advanced indirectly heated carbonate looping process. I will explain later a bit more about the process itself. What is the overall aim of the project? That's develop concepts of this indirectly heated carbonate looping process for CO2 capture from lime and cement plants. I think I don't have to explain why we have to capture CO2 from lime and cement plants. They are one of the major emitters, and we have also this process CO2, which has to be captured, and there's no other means to do so. So the objective is to test this new technology at around 300 kilowatt pilot plant, prove the feasibility of utilizing spent sorbent for other purposes, and like, for example, the cement production, also the lime production process, develop novel concepts for the reactor system to assess risk, economics, environmental impact, and to design a demonstration plant for the technology. The consortium, as already mentioned, 3 different countries. We have, again, a lot of academic partners, also industrial partners. I just like to highlight the contribution or the involvement also of end users, like from cement industry, the Dückerhoff company, and also from the lime industry, Loast and CAO Helles. And also we have some technology providers like ThyssenKrupp and also Calyx, you may know from the Lilac project. Here is an overview of the indirectly heated carbonate looping process. So it's a post-combustion technology, but using calcium oxide as a sorbent. So the flue gas, the CO2 in the flue gas reacts with the calcium oxide and the carbonate at around 650 degrees. Then it's transferred to the calciner for regeneration at a even higher temperature, around 900 degrees. And let's say the standard carbonate looping process is using combusting a fuel inside the calciner in combination with oxygen to regenerate the CO2. But the indirectly heated process uses heat from an external combustion chamber, but this heat has to be transferred into the calciners, and we are using heat pipes to do so. And the off gas contains CO2, and this again has to be introduced in the carbonator to be also decarbonized. So there are a lot of positive features of this process. The first one, the sorbent, is a natural material, quite cheap, and it can also be used in the same process like cement lime production. Then we are utilizing the heat at a rather high temperature, 650 degrees, 900 degrees. So the heat we put into the system, it's not lost. We can use it for electricity generation, for example. And compared to the standard carbonate looping process, here we don't need any oxygen, which is usually needed for the calcination. We have no impurities in the calciner. We are not diluting the sorbent. And we have almost pure CO2 here at the exit of the calciner. Yeah, we have defined some key performance indicators. The CO2 capture efficiency here, again, 90%. So it's not, for carbonate looping, it's not feasible to reach 100% due to some equilibrium limitations. There might be possibility to go even higher, maybe 95%, but this is always accompanied with some additional energy penalty. Yeah, CO2 purity, we can reach almost 100%. Net efficiency of our power generation, since we are working at high temperature, we can use up to 45%, like in power plants. Sorbent utilization, I think we could use more than 90% of the material in the production process itself. CO2 avoidance cost, our target is 25 euro per ton, and net negative CO2 emission, that's because we are aiming at using here waste as fuel. Okay, yeah, the work packages, I go only very briefly here through this overview. We have a work package on process development and pilot testing, then reactor development to improve the reactor system, to assess the process, then design of demo plant, and in work package 6, here we're looking at how to combine a direct separation technology developed by Calyx with this carbonate loop, indirectly heated carbonate looping. Then we have dissemination and coordination. I will briefly go through the work packages, or some results we have achieved so far. So the project is running for more than 2 years. We have some delays due to the COVID, yeah, for work package 1, we have already developed designs for the process for both lime and cement industry. So there's a quite high potential for power recovery, but we also saw that there are some difficulties, challenges, and that's one thing is we wanted, also one option is to use cement raw meal as a solvent in this technology, and there's a decrease of the reactivity due to some reactions taking place at a high temperature. Then the heat integration is one critical aspect here, because we have to use additional heat, and we are placing more or less a power plant beside a cement plant. And the heat we are introducing is significant. So in the end, probably it looks more like an additional or a power plant with some cement production. So we have to find a good balance in this respect. Yeah. And component development is still an issue here. Yeah, pilot testing, this has been quite a lot delayed from original planning. We should have now been able to present a lot of results, but due to especially late delivery of components, we had a rather large delay. So, but finally we managed to do all the construction work for the pilot plant. It was an adaptation of an existing plant to get a more realistic flue gas, for example. We have some first results. We completed one test campaign, managed to get stable circulation and very good heat transfer through the heat pipes. Also managed up to 90% CO2 capture. We are not fully satisfied with the results, but we have 2 more campaigns to improve even the performance here. Okay, yeah. What are we going to do with the results? We have collected a lot of samples, solid samples from sorbents. We are currently assessing the usability of the spent sorbents for the lime cement production. Okay, yeah. For the model, for the reactor development, we have developed reactor models and also CFD model for the fluidized bed system. We are also have developed concept for solid-solid heat exchange. That's to preheat the solids entering the calciner to save some heat requirements, and to improve the heat pipes itself, the inner structure, the heat transfer inside the heat pipes. Process assessment, we have done. We are still in progress of risk assessment, and techno-economic assessment is also in progress. Here, this work has also been done from Ulster University. Yeah, he's also involved in the same project here. So the first figures we received are quite promising. So when we increase the share of waste as a fuel, then we also can decrease the capture cost, because waste usually we can get even a refund for taking it as a fuel. Life cycle assessment also in progress, and also here the use of a waste is beneficial. Design of a demo plant, we have defined, let's say, the position of such a demo plant, also basic layout, and decided on a beneficial size in around 3 megawatt fuel power. Okay, for the direct separation roadmap, together with Kylix, so they have investigate several options how to combine their process, the direct separation process, with our process, and the heat and mass balances are still in progress. Yeah, finally, dissemination. We have a website. We have published several newsletters. We had already 1 public workshop, and there will be an additional one with the Act to SEM project, which has already been announced. We have not so many, unfortunately, not so many publications, but we are currently preparing a lot of them, and hopefully increase, at least double the number of more, not only for the papers, not double, even maybe our goal is to have at least around 10 papers and even more presentations. So. Okay, next steps, I go very briefly. We have the pilot test finished, then analysis of sorbents, model validation, process optimization, and use all the data for the final assessment of the process and also for the final design of the plant. So thanks for the funding and for the attention. So thank you. I think there's not much time left.
No, thank you very much. I would indeed propose to remember this guy and address him when we have drinks. It has been a long day, ladies and gentlemen, for us, but we are now moving to Canada, where the day has only started. The next speaker should be Tim Stauft from CREATE. And he's talking just from Canada on the CREATE project.
Super. Thank you very much. And I really appreciate the opportunity to speak to the group here from Canada. Sunny day here in Calgary. The CREATE project is the carbon reforming to economic additives for transitioning into emissionless era. It's all about testing the applications of our technology, Carbonova's technology, in the cement industry. Our partners are Wholesome from France, CCUS from Switzerland and France, the University of Calgary, as well as a couple of energy producers based here in Calgary. And our funders obviously are ACT from Norway, as well as the government of France, and a group called Emissions Reduction Alberta, based here in Canada. Hopefully I can move my slides. Okay, okay, this is gonna work. There we go. So like any company, we have to have this small print that the lawyers insist on having. Apologies for that. Just quickly get through that. Okay. So to start with how Carbonova got started and why we got started, this first slide is just a look at all of the number of companies globally that are focusing on net zero targets. And it's really because of that Carbonova, oh, my apologies, it's a little bit slow. There we go. Okay, so a number of companies globally that are focusing on environmental goals and net zero by 2040, and that's really how Carbonova got started. What is our technology? Our technology is one that takes greenhouse gases that normally are damaging to the environment, and we convert them into solid carbon in the form of carbon nanofibers. And in that process, also produce water, and as well the reaction, which is a catalytic process that takes those greenhouse gases, is exothermic as well. So in essence, we're creating heat that can actually be managed within the process to convert the methane and the CO2 to solid carbon. What is the carbon market? The carbon market is really composed of three different large elements. Carbon black, which is the lowest cost to produce as well as the lowest quality. Carbon fibers, and then finally nanofibers and nanotubes. The Carbonova advantage is that we produce the highest quality of carbon, the nanofibers and nanotubes, but our cost structure is quite low. So our cost structure is similar to that of the production of carbon black. So in essence, we believe that we'll be able to access the largest markets. The size of the circles there are intended to indicate the size of each of those markets in the terms of each of the carbon segments. So Carbonova can access, and its technology can access the largest markets at the lowest cost. So we think we can have a material impact on not only the environment, but the market for carbon fibers themselves. And from a business perspective, we do have patents on our process, and we believe that we can repeat our process in multiple locations, but after we get through this next phase of validation with our partners in the cement industry. So what have we done so far? You can see on the left-hand side here a microscopic image of our carbon nanofibers. This is directly from the Raman's microscope that we were able to purchase as part of this project. And we've been able to analyze our project, put it into solutions. In our case, we used an aqueous solution to mix our carbon nanofibers and transport it to customers. There's also an opportunity to take our product in and put it into organic solutions for other applications in plastics and other potential applications as well. This is just an overall diagram of our project with Create. You can see that the way you heard a couple of other talks here this morning, or this afternoon, I'm sorry, this afternoon where you are, around carbon capture and taking the CO2 out of the cement plant. Our project is really just a little bit further downstream. So we take that CO2 that is removed, combine it with methane to create our carbon products. And then those carbon products can either go into the existing carbon black market, or it can actually be mixed to the cement. And in mixing with the cement, that cement, it now has higher electrical conductivity and higher strength. In essence, the carbon nanofibers replace the steel rods that would typically go into cement to add strength to the concrete. Okay, we'll get to the next slide. So what are we trying to do? We're really trying to combine our IP and technology, which we do believe we have line of sight to commercialization. We've got a strong team with strategic partners, as we mentioned, ANICA and Holcim being one of the largest concrete companies in the world, as well as CCUS, which distributes products globally as well, both Fortune 500 companies. We think there's extraordinary potential value beyond just the concrete business. And we believe that there's an opportunity to diversify the economy here in Alberta, but also apply our technology around the world. That is it. I think there's a couple of slides that I presented previously, or that I sent, that obviously didn't make it into your package, unfortunately. What I can tell you in terms of our next steps, we are looking at integrating our process to a cement plant with safe handling procedures. We're also looking at the technical specifications associated with the dispersion of our product, the carbon nanofibers at a bench scale, and then carbon nanofibers at an industrial scale. Like many of the other technologies that have been discussed, we will be putting together a life cycle analysis for carbon nanofibers. And then finally, we'll be putting together the business case for our commercialization. And all of these incremental steps will be taking place between now and 2024.
Okay, thank you very much.
Thank you.
Are there any questions to Tim? Yes, here's Susanna.
Hi, Susana Garcia here at Good University. I was just curious to understand how much the contaminants that come from your CO2 capture process, or whatever is left in there, affect your process. Do you have a minimum purity, or can you maybe elaborate a little bit on that part? Thank you.
For sure. That's an excellent question. So far what we've done is we've developed our project at a pilot scale. So we're using purchased gases. We have introduced some contaminants to see how it impacts our catalysts, and hydrocarbon impurities do not seem to be a problem at all, from C2, C3, C4, and also nitrogen and hydrogen. So they don't seem to have any impact. At a commercial scale, we may have to look at sulfur removal to the extent, depending on the source of CO2. Otherwise, really the impurities, like if we're at 90% CO2 as an input, for example, all that does is impacts the size of the reactor vessels and possibly the efficiency. But overall, we don't see the contaminants in the feed gas as being a material problem for us.
Thank you. There's another question, Greg.
Thank you. Greg Chass, Queen Mary, University of London, fellow Canadian. Quick question, it's a two-part question. So you had said raises strength. So the first part is that compressive strength or tensile strength. Second part of the question, at what expense to fracture toughness? Because strength and toughness are in perennial conflict. If you raise one, you usually lower the other. So just,
right.
That's the question.
Yeah, so what we've done so far is the analysis we've done is its tensile strength, and you're right, it does impact other forms of strength as well. That's really when we do the more detailed additives, adding our carbon nanofibers to concrete, we'll be able to answer that question a lot better and obviously optimize the mixture levels so that we get the best possible economic result for the concrete cement companies.
He's satisfied, he's happy. Well, I would say I'm happy too. It has been, thank you very much for your contribution here, Tim, and give him another applause.
Sorry to be between you and drinks.
I would like to see everybody on that has been presenting this afternoon on the stage here, so that we can have some sort of wrap up. Then we will advance to have everybody that has been presenting on the stage, just to get the whole picture of what we are together in ACT. We've seen very many presentations this afternoon. We've seen presentations on well technology, on usage of CO2, monitoring and cement. It was amazing. It's such a broad area that we are now working on together. And well, please, presenters of today who are still here, join me here, and we will, I think, just take a picture, and then Raniel and all the others come up as well. So please, the presenters of this afternoon first.
I would say for a change it will be more women than men. I'm looking forward to that.
Anna says it will be more women than men. Oh, it's, well, I'm not so sure. Yeah. Yeah. Getting there. Equals? No. We've lost. Okay. 3-1. Oh. Oh my.
She's okay.
Okay, she's okay. Okay. Everybody that has been presenting, please. And Raniel, our coordinator. So we're bringing up more women now. Oh yeah. Oh, could you please?
8 women.
Could you please turn down the projection?
Yes, come for that. Kneel down. No, we can just switch.
The short ones in front.
Direction and smile.
Okay.
Thank you very much.
Do you want to say a few words, Raniel? And I'm sure that Jan is also going to say a few words after this because of the excursion tomorrow. Thank you very much for being here.
Thank you, Gerdy, for chairing this last afternoon session also. This has been great. There was a guess whether there were more women than men on stage. That might have been a dream. I don't know who came with that suggestion, but there have been 8 female presenters of the projects today, and Gerdy and me in addition, but even though there are more men. But what is really good to see that there are even more female persons involved in this type of projects and technologies, which is very, very promising, I would say. Also in terms of it covers a broader group of people and users, of course, and we reach out to different groups also outside this ACT family. So this is great. But I'm so happy with having the possibility to meet all the projects here live and those being on virtual stage, if you could say. It has been extremely good, very extremely good. And we now have good ideas for how we can progress further on. And thank you to Jan and Erika also for organizing this so nicely, all the great guys over there, the black man. They've been very, very good. But also I'd like to thank Harry and Lee for having kept track with the organizing committee since a long time back and having arranged everything so nicely. Thanks to all of you. Hope to see you tomorrow.
Yes, and please remain seated. I have an announcement for those who are coming to the excursion tomorrow. Some practical things. First, I feel a bit ashamed that I'm a male, but in the organizing committee, I balanced to the male side. So that. So tomorrow we have somewhere. Oh, what should I do? Okay. Okay, let's try. So we have we have 2 excursions basically, and then one thing you see here in yellow is bring your ID. This is important. We have 2 excursions, and how does it go? We leave in one bus from the SS Rotterdam tomorrow at 8:25. So it's in front of the door, in front of the ship. You need to be checked out, bring all your stuff, because we're not coming back here. The bus goes first to Delft, then the people that go to the Delft excursion, which is the capture excursion, they get out of the bus. The rest goes in the same bus to Rijswijk and have the Rijswijk excursion. Then the bus goes back to Delft, pick up the people from Delft to Rijswijk. So it's a bit complicated, and for that reason I made a map here of the Netherlands. You see on the left where we are, you recognize the Netherlands. It's a small country and the trip is even smaller. But if we make it a bit bigger, we are, and now I was looking for this very nice thing, who cares? We are here and we move to Delft with all of us. Then people get out, go to Rijswijk with the second half of the people, they get out. Both get the excursion, and the bus picks up the people from Delft and bring them to Rijswijk. Then this is a slide which you can make a picture of, because it's important for you. Because when we go to Delft, the address is Leegwaterstraat 44 in Delft. So if you miss the bus tomorrow morning, which can be done. But then go there for yourself, and then you can join into the program again. After that, we go to Rijswijk. The address is Lange Kleiweg 1D in Rijswijk. Also there, you can go by car if you want. Don't make a photo yet, because we're not finished yet. The excursions, they finish in Rijswijk, and when you are in Rijswijk, there is no transport anymore from us, but there is a train station which is on 6 minutes walk. And later on, if you make the picture, you can see where you have to walk, and you can ask the people. Then you're in the train station. The train goes to Schiphol and wherever you want. If you have questions, call our Geke. And once more, bring your ID, which is a driving license or a passport. So you can make a picture. You can make a picture of this one. Also, after that, we will keep this slide on the screen. There's one thing more I like to say. I'm on all that pictures. Because tomorrow's excursion, as I said, at 8:25 the bus is leaving from the SS Rotterdam, which means 8:15 we should be boarding into the bus. So get your luggage, I repeat once more, get your luggage, check out for the hotel if you want to do that, but go to the bus at 8:15. And when I say 8:15, you might think 8:30, not 8:30. You might think 8:25, not 8:25. I use this one, okay? Not 8:25. You might even think 8:16. No, it's 8:15. Yeah? I know you people, it's 8:15 sharp. Sharp. And thanks for the logo, sharp. See you tomorrow. There are drinks now already there. We go back to the previous slide. Can you arrange that? So if you want to make a picture, it's nice to have this. You know the place where to go. And yeah, then you don't need the previous slide. That's what you mean. Yeah, good. So see you at the drinks.